I'll officially kick it off. Hi, everyone. My name is Andrea. With me is Vishal, Jordan, and Alex. Jordan and Alex will be taking the stage today and talking all about the interesting stuff. But what I want to do is give you some context about what we're doing here today and what you can expect from this session. So earlier this year, the consensus team that's working on Flow rolled out a major upgrade to the consensus algorithm. And that upgrade not only reduced the transaction finalization time by 30% and enabled faster automatic recovery from network partitions, attacks, and upgrades, but as part of that upgrade, it also laid the foundations for a bunch of improvements to improve attack resilience and also processing speed for all non-consensus nodes, including observer nodes, which anyone can operate without staking. So in other words, the node software has become a lot more resilient in handling bad actors on the network. For those of you who know the term Byzantine fault tolerance, this is a perfect example of this improvement. And we're excited to share that these improvements will be rolling out in the June network upgrade, currently scheduled for June 21st. So in today's talk, we want to give a bit more detail about not only the improvements thus far, and also do a little bit of a recap of the Flow architecture, but also show you all of these improvements in action. And so the way that we've divided the talk today is first, Alex Henschel, who's an architect of the protocol, is going to give us a general overview of the Flow architecture and just generally set the context of how all of this fits in. And then Jordan will take it away with a live demo, and he'll be running two versions of the network, the current version and the upcoming version, and he's going to simulate a form of attack and show you how both versions of the network will respond to it. So should be pretty exciting, and I can't wait to see it myself. So without further ado, I'll let Alex take it away and set the stage for everyone. Alex, over to you, and I'll leave the floor to Alex Henschel.
Good morning, good afternoon, good evening. Yeah, thank you for joining us today. So, and thanks, Andrea, for the kickoff. So, the first thing I'm gonna do is briefly recap Flow's architecture. So we're all on the same page and sort of have the context for the second topic, which I'm then going to talk about, which is the consensus follow upgrades and what they mean and a little bit on how they work. Yeah, let's see how we do here with time, and I might adjust like the depths of or how far I get into stuff depending on how we do on time. All right. So Flow's architecture in a nutshell. So the biggest thing about Flow is that it heavily embraces pipelining. So you start here with inbound transactions, and they first go to several groups of nodes, which we call collectors, and they do essentially nothing else than consume the incoming transaction, put them into batches, and then publish those batches. Those batches of transactions we call collections, and one group of nodes which creates such a stream of batches is a collector cluster. So and Flow has multiple of those collector clusters, which allow us the ingestion of transactions to scale horizontally, far beyond the capacity what any node individually could consume in terms of data per second. Okay, so those collections, the clear text collections, so the full data goes directly to the execution nodes. I'll come back to those in a second. But the hashes of the collections, we call those collection guarantees, go to the consensus nodes. So the consensus nodes essentially only have to worry with or deal with the assigned hash of a large batch, and the signature is there so that consensus nodes know who has created that batch and sort of who has signed and promised to keep this batch available. In a nutshell, this works quite similarly to what Ethereum is now considering as data availability shards. Flow had that from 2019 baked in. So this concept of essentially smaller groups of nodes locally storing and maintaining data and giving it to the other parts for processing later. So yes. So the execution nodes then, the consensus nodes package those references to the collections. They package those in blocks, add a little bit of other messages in there to orchestrate the entire flow of the protocol, and then those blocks are published. They go to the execution nodes. The execution nodes pick up those blocks and just run the computation. Exactly what's listed in the blocks. And then the results of the computation, the execution results, those go to the verification nodes, and then the results are ready and approved. So in a nutshell, that's flow. And on the outside of that entire ecosystem, there's our access nodes, and they're responsible for piping transactions into the system and piping the the resulting results, publishing or providing those to the remaining part of the internet, essentially. So I said earlier that is a pipeline processing, or that's a pipeline processing approach. There's a sort of higher level abstraction of this process I just talked through, shown here. And so the collector and consensus together, that's the part of the pipeline which does the transaction linearization, which is nothing else than just a technical term for determining an order. And once that order is determined of all the inbound transactions, they're streamed to the execution nodes, and then the results are streamed to the verification nodes. And so one very critical part of this pipeline, or one critical insight here, is that once the transactions come out here in a linearized order, then the execution nodes, or what they do, is fully deterministic. The result might not be known yet, but it's certainly unique and only determined by what the consensus and collector nodes here, that information they released. And so realizing that whatever the execution nodes do, their work is essentially fully deterministic, while the work the collector, consensus, and verification nodes do, that's highly decentralized. That allows us to do a relatively optimal trade-off in terms of how much redundancy do we want in the system? Because redundancy generally is good in the system. It makes your system more robust. It makes your system a lot more resilient to censorship, and provides generally openness of the system. But it also has a price, right? For every machine you run, you need the energy to run the machine, and you need the relatively high cost resources and energy to actually produce that hardware. And in a world where we're living now, where we have to be sustainable with our resource consumption, being deliberate of where do we actually utilize redundancy in a system and where does it not help us and just cost us, to consider that is super important. And so this is essentially here the trade-off for flow. And so what this figure here illustrates is that in the transaction linearization phase, so consensus and collector nodes, we benefit a lot from redundancy, right? It makes essentially our system decentralized. It makes our system robust, both against just like benign failures as well as malicious actors in the system. So redundancy in the transaction linearization step of the pipeline is great. And it also doesn't cost us very much, right? Consensus and verification collector nodes, they're comparably cheap to run. But the execution nodes, they are very, very large nodes in our design. They're essentially small data centers which just horizontally scale and provide the entire execution sort of horsepower behind the system. And there you can imagine, right? If you have 6 data centers or 50 or 100 data centers, that makes a huge difference. Both how much energy you consume as well as how much hardware you need for the entire system to run in the first place. So here, the cost of redundancy is high, right? And more importantly, the benefits we get out of it are relatively limited in the pipeline architecture, because as we said earlier, the execution nodes essentially do nothing else than dumb execution. They don't decide anything. If they if they decide to go malicious or not, if they decide to go malicious, the only thing they can do is essentially publish a wrong result, which will be rejected, or publish no result. So they can't really essentially undermine the system on a larger scale. The only thing they can do is stop contributing honest results. So that's the reason why for the execution step, redundancy is or the benefits of redundancies is relatively limited. And so that leads us to the following trade-off in Flow. So we say we have a high level of redundancy for our transaction linearization step. There we get all the benefits of decentralization. For the execution, we focus the execution in a few nodes. There we get all the benefits and also scalability of like highly localized data and highly localized computation. So essentially locality. And then again, in the verification node and access node steps, where the data comes out of the system, there again, we add a lot of a lot of redundancy for decentralization and robustness. And that essentially gives us the best of both worlds, right? It gives us the full robustness, resilience of a fully decentralized system, and it gives us the energy efficient or energy efficiency, resource efficiency of low redundant computation here in the middle step. Okay, and so that essentially brings me to the reason why we built Flow the way we did, right? We looked at various blockchains and said, well, okay, you can scale that, like second generation blockchains. They have a lot of scalability beyond like what Ethereum and Bitcoin still has, or Bitcoin still has in their early days. But there are limits to that, right? If you look at any other blockchain which has a single node design, meaning all nodes do exactly the same thing, then I think it's going to be very challenging to convince your node operators that each of the machine needs to hold 1 petabyte of world state. Within Flow, the 1 petabyte of world state would only live within the execution node, so it would only be replicated 8 times. People can access it through verification and access nodes, but the core replication factor is only 8 for the 1 petabyte of data. In like one or single node architectures, those replication factor for the world state is often in the hundreds, sometimes even in the thousands for the mature systems. The other thing is just the computational hardware, right? Imagine you want to process 1 million transactions per second. They can be highly parallelized, yes, but still processing 1 million transactions per second or even beyond that is going to require many, many CPUs. In Flow, the execution nodes will easily provide something like 1,000 CPUs per execution nodes, so per small data center, 10,000, 100,000 of CPUs, no problem. Within a single node architecture, that's essentially intractable to have more than, like, I don't know, whatever fits in a single strong server machine. So you see here that in Flow's architecture, scalability becomes possible, which is sort of fundamentally limited in the single node architecture. And that's the reason why Flow has decided to take on the, I guess, the larger complexity of separating all those functions out into different nodes and not just going with a single node design. Because we believe that in the end, this is future proofing, right? It's for every developer, it's providing a strong system which can scale beyond what a single machine can do. And we get that at the sort of energy and hardware efficiency factor of roughly 160 to 260 compared to 100 plus or 1,000 plus in single node architectures. And yeah, so So that's the reason why Flow has a sort of more, I guess, refined, finer-grained architecture. And let me talk to you a little bit about the sort of, I guess, the timelines of developing such a system. And let's address that elephant in the room, right? Because fact of the matter is, it's taking us a while, right? We're building and building and building, adding features, and other blockchains seem to be somewhere ahead. And yeah, sure, if you're the right guy building a small rocket, just want to launch a few kilograms of weight into space, you don't need a super sophisticated system, right? And that's, in my opinion, where a lot of the other sort of chains are in the ecosystem. They've built a small, sleek system which scales to and serves the sort of load which we see today, right? But the question is, how will that work if the load goes 100x or 1,000 grows by 1,000x? Because then you can't just say, well, okay, I'm going to put several sort of small rockets. It's going to cost you to scale all your load across multiple shards. And we haven't seen really a system which does that very efficiently in practice. Only thing we've seen is promises that will work out. In contrast with Flow, we've decided to invest a lot of time into building like the foundation to really build a scalable system. And yes, it's taking us longer, right? But we're building a huge sort of rocket which can lift tons of cargo load into space in one go. And the big things you all get is a system which is heavily focused on usability. We try to absorb a lot of complexity into the system so that the developers don't have to deal with the complexity and work around the complexity. So for instance, Flow has Cadence, which is a resource-oriented programming language. It makes it very easy to manage resources and control access. We have highly composable or a system which has highly composable transactions and highly composable smart contract language, meaning all the smart contracts can easily interact. You don't have any extra cost of cross-shard communication or having to deal with different rollups. In Flow, that's all one huge computation state. We have access layers or the access nodes and observer nodes, which anyone can run for highly scalable data egress. Our execution nodes are or our pipelined architecture, including the execution node, allows an excellent throughput of the mature system. The execution nodes can provide large world states, manage petabytes of world state. It's very energy efficient, as I said, about a factor of 5 more energy efficient, 1 order of magnitude more energy efficient than single node architectures. In our system, latency is a little bit of a trade-off factor, but we still have a cutting-edge consensus algorithm. You might have followed what we did earlier this year. Flow's latency is very robust under load and malicious actors. So overall, it's a really strong package, and it allows this in combination will provide a scalable system with a lot of user features. Okay, so essentially the core of the message is Flow is solving the scalability challenge now. Over the last few years, we've worked from a centralized network to a decentralized network, and Flow at the moment is fully decentralized, and we're working our way towards a fully autonomous network operation. That means that humans are only involved in the protocol for adjusting protocol parameters or, well, of course, operating the nodes. And that's the journey we're heading. And if you're thinking in that realm of what would the network have to respond to autonomously? Well, for instance, malicious actors, right? So that's the domain of Byzantine fault tolerance. You have to do slashing, so punish people or malicious actors for malicious behavior. You need automatic performance-dependent rewards, extending permissionless participation, trustless data retrieval. That's all topics we're consistently working towards. And in a design with 5 nodes, of course, it's going to take us a little bit longer, but we're sort of working our way through there and really trying to build that huge rocket which can lift a lot of cargo into space. Okay, so let's talk a little bit about the topic of Byzantine fault tolerance. And so that's roughly the second part of the conversation here, where we're getting into the consensus follower. So the consensus nodes, in a nutshell, they orchestrate the network. They produce blocks, and the blocks are consumed by the other stake nodes, collector, execution, verification nodes, access nodes, archive nodes, and then the blocks also are handed to the unstaked network, observer and archive nodes. And what all those nodes do is they verify the blocks to a certain extent. So and that's what the consensus follower does. So it's a little well, computational module which runs in each of those nodes and allows any non-consensus nodes to track consensus progress in a trustless manner. Very important. And so I think I'm going to skip a little bit over the details here. So in a nutshell, the consensus follower optimizes the way how it verifies blocks. So in blocks, we have the quorum certificates, which are an aggregated form of the consensus votes. So whenever a block has enough consensus votes, they're 2/3. They're aggregated into a quorum certificate, or in short QC, and that QC goes into the child block. So you see here that the QC for block B is actually in B's child block. And so the core insight here is that the QC attests to the validity of the block. Yeah. So the QC E here in this example attests to the validity of block E, even though the QC is included in the child block. And that means that consensus nodes have signed off on block B, C, D, E in order to produce this QC. So by verifying that this QCE here is correct, you already know that all the ancestor blocks have been approved by the consensus committee. And so this insight of saying, oh, I only have to verify one QC, and then I know that entire fork is valid and has been or is considered valid by the consensus nodes, that's a huge advantage. And that underlies essentially all the optimizations we've done in the consensus follower, and we've restructured the consensus follower to take or to utilize those insights for performance and resilience purposes. Okay, so what the consensus follower does, it shields the higher level logic from any malicious blocks, and it has vanishing computational footprint, which is also a really interesting topic. Yes, so the vanishing computational footprint, you can use that for light clients. I won't get into more details here. You can read up on that in our blog post. The link is here at the bottom. And the other thing is that it allows the consensus follower to be more resilient against various Byzantine attacks. So in this particular case here, that's just an example. It's a storage consumption attack. So essentially, somebody is filling up the storage in your node with nonsensical data, and it could be used as a data poisoning attack. And the idea here is that a malicious node, a malicious consensus node, we assume such things will exist in the system, will just publish a bunch of conflicting blocks. And in the current case, the attack we're demonstrating today, the parent block is unknown. But even if the parent block is known, the consensus follower, the old consensus follower, would just save all those blocks. So if you have a single malicious node in the system producing tons of garbage blocks, the old consensus follower would store them to disk, potentially propagate them, and the new consensus follower doesn't store them to disk. The new consensus follower caches all the conflicting blocks in a separate cache, and it waits for one of them to be certified, so receive the QC. That can only happen, or consensus rules guarantee that only one of the many conflicting blocks can get certified. So the consensus follower, the new consensus follower, only stores certified blocks to disk, which do not pose any risk of storage exhaustion attacks, while the old follower would just store all the blocks to disk, and it would also cache them all in a relatively, in an unbounded cache, meaning that you could also just flood the logic with a lot of blocks. And specifically, if the parent block is unknown, which is the attack we're simulating today, the old consensus follower will just keep those in the cache. We'll have to do a lot of maintenance work to manage those blocks, essentially all that garbage data, it's being consistently fed, and that will come at the cost of actually executing its functionality. And so what we will see in the old, that the old consensus follower, it won't manage to keep up. It's just overwhelmed by all the garbage, while the new consensus follower very efficiently handles that. It detects the garbage, so we can raise flashing challenges. And so it's first unaffected. It detects attacks, it publishes those, or it notifies about attacks it detects, and thereby makes the entire system a lot more robust. Because remember, the consensus follower runs in all those nodes here. So it's essentially the first line of defense within those nodes against malicious actors in the consensus committee. All right, that's it from me today. Thank you very much. Here are two references. So the first one is about our consensus work more broadly, which we did over the course of the last year. And the new consensus follower we published, or we rolled out to mainnet in January of this year. And the second blog post talks more about the consensus follower in detail. That's the work we're demoing today. And that work will hit mainnet next month. So super exciting. Yeah, stay tuned, and I'll hand it over to Jordan. Thank you.
All right. Hey, everyone. Thanks for that, Alex. Just going to present here. Okay, empty terminal window. Perfect. So like Alex mentioned, what we'll be running here today is an attack against the same attack running against both an old instance of the network, which is the current version, version 29, and the new version, which will be rolling out to mainnet next month. Just going to start by bootstrapping both networks here. So we're using the same configuration on both fairly small networks. This is using the LocalNet tool. We're going to start them both here. So both these networks are just running with 2 consensus nodes and 1 verification node. And we're going to open up a graph of the network progress. This is showing the latest finalized block height, which is being reported by either network. So we can see all these little dots here. They're just getting started up. There we go. So this is kind of what we expect from a normal, healthy network. Finalized height steadily increasing over time on both of these. By the way, on the left in both the terminal and here is the old network, and on the right is the new network. Right, so both are increasing steadily. And now I'm going to essentially turn on the attack. Oops. So I'm going to adjust the network configuration here, and we're going to set a flag, which obviously doesn't exist in the real software because it's an attack. And that flag is going to tell the malicious node to start an attack on the target node. So we're going to find verification node number 1 here, grab its node ID 38DC And we're going to set this flag unsafe follower attack target 38 DC. Okay, so that's telling the consensus node to begin initiating this attack on the verification node. I'm going to save that file and then restart the consensus node so that'll take effect. And then we'll do the same on the new network, which is resilient to this attack. Find the verification node. Its node ID is EC135. EC135. All right. Save that file and restart, and we should have the attack running on both networks. And it does take a little bit of time for the attack to take effect, so I'll explain exactly what's going on in the attack while we wait for that to happen. So the attack module is sort of attached to the engine, which normally is the consensus node is using to send out normal valid blocks, which are produced as a result of it participating in consensus. And what the attack module does is once it's enabled, it will find the latest finalized block and then create a whole bunch of malicious blocks, which are ahead in view terms, meaning that at first glance, a follower is not 100% sure whether they will eventually be valid or not, but constructed in such a way that their parent is unknown. The parent ID field is essentially a garbage. So they're effectively unconnected blocks. They don't connect back to the rest of the valid finalized state. And this is a particular example. There are a few more, but this is a particular example where the old follower engine is vulnerable to the kind of attacks that Alex mentioned. It's not able to detect that these blocks are invalid, whereas the new one is. So let's check up here. Oh, and we can already see. So again, we're looking at the finalized block height here. This is the left-hand side, so this is the old network, and this is the verification node. So the attack's been running for about a minute or so, and we can already see the verification node is starting to fall behind. It's behind by about 50 blocks right now. And we can take a look at the other network, and everything is pretty much normal. There's a little bit of jitter here, but that's relatively normal from just nodes reporting different metrics at different times, and it tends to kind of clear out over time. But if we give it a bit more time, we'll see that this gap essentially continues to grow and grow. We can also look specifically into what's going on the verification node that's being attacked. So we can look at how its memory usage is being affected. And this graph here is showing how many proposals, essentially all of them are invalid attack proposals, of course, are included in its mempool. And you can see it's growing very, very quickly. Dealing with all these proposals is what is causing it to fall behind. And we can also look at a sort of network-wide impact as well. So since we only have one verification node in this example, and that verification node is being pretty much slowed to a halt, that verification node is unable to verify the execution results that are being produced. So you can see here at the bottom, of course, the verification node is impacted, but in terms of sealing, the whole network is actually impacted as well. And we'll go back to that finalized view. So this is all in the old network where the attack is sort of successfully negatively impacting this verification node. If we jump back over to the new network, we can again see everything is pretty much fine. There isn't really any impact at all. And yeah, we can check the sealed height as well. Again, steadily increasing kind of normal behavior there. And we can also see, if we look at the verification node's logs, so this is on the new network, the verification node is the one which is under attack. We can see that it is detecting and logging through a sort of slashing challenge hook, the fact that it's observed all these invalid blocks. And there are quite a few, tens of thousands that are being logged here. So this is new as well. In addition to sort of having the attack not negatively impact the performance of the verification node, we can now we now have the hooks in place in the software so that these are being detected in all these additional cases where previously invalid blocks weren't being detected. So right now it's just logging, but in the future this will be where slashing challenges are raised. And in that case, if a slashing challenge is raised, this attack can be shut down very quickly because the malicious node can be ejected from the network. Okay, so that's pretty much all I have for the demo today. We'll take one last look at how both networks are doing. So here's the new network, and here is the old vulnerable network. I will also show one last thing, just because this obviously takes time to happen, and we don't have enough, but this is an example of this same attack running for about 4 hours. So this is from about noon to 4 p.m. and you can see the impact kind of just gets worse over time. It pretty much flatlines the target node. And similarly for the memory usage. And this is the new version of the follower, the new network running for 4 hours with the attack running the whole time, and there's no noticeable impact. All right. So yeah, that's the demo. Thanks, everyone. I'll hand it back over to Andrea now.
Thanks, Jordan, and thanks, Alex. Great stuff. I'm actually I shared the blog post in the chat already. So what we can do is maybe open the floor for questions. Feel free to either type it in the chat, or you can use, as Jordan affectionately calls it, the triangle, square, circle button on Google Meet. And there's a Q&A functionality there where you can ask your question as well. So if you have any questions or any comments that you want to make, feel free to write it, or also obviously feel free to unmute and say it and just ask it.
Hi, everyone.
Hey, Daniel.
Hi. Yeah. So, Alex, very good presentation. Jordan also. So, what's like you talk about newer chains. So, like, I saw like Flow implemented Jolton that was on it was on Move, I think, before. Like, I think Aptos had Jolton before, and now they have like Narwhal. It's like, does Flow, or is there a plan for Flow to have like parallel execution of transactions? Because I saw something like, for example, on an Aptos interview, they were announcing like there was a question about how many TPS, even though TPS is like a, how can I say this, just like bragging number. They were like, okay, what's the TPS expected, or at least theoretical TPS on Aptos in 2025? So averaging was like, okay, so we're targeting 1 million TPS. So at least what's like, of course, it's like Visa has like 5,000 TPS maybe, so like payment processor. So what's the theoretical at least TPS that you guys are targeting for? Maybe it's not even a number, but I don't know what's, yeah.
Yep. Thank you, Daniel. Very nice question. So maybe let's start from the back, right? What's sort of the bragging number? Well, our bragging number is we've written that since a very long time in our papers is 1 million TPS. The important thing is that for Flow, you can ingest more transactions than a single node has the bandwidth to ingest, right? Because for us, not all transactions go through the consensus committee. They first go to the collectors, where you have, and they batch them individually, and then only the batches, sort of the hashes of the batches, go to the consensus nodes. So for us, it's roughly 1 million transactions per second. Potentially, we can scale beyond that. So that's for the transaction linearization sort of pipeline, right? I think, in my opinion, more important question is, well, okay, so we can order or linearize all those transactions. Can we execute them, right? And that's sort of, in my opinion, where it gets difficult, right? Because now suddenly you need to have a node who can one node or multiple shards of nodes who can sort of crunch through all that computational request. And that's the execution nodes in Flow. And you're right, we absolutely need parallel execution. In fact, we're sort of very far through that process. It's a non-tricky or a non-trivial process. It's largely the same sort of approach as what you see in any distributed databases, and what Aptos has implemented with their software transactional memory, or most other blockchains implement. It's essentially an optimistic heuristic. You just execute many transactions in parallel, and as you go, you find where the conflicts are. And then if there's a conflict, you look at, oh, which transaction should have been executed first, right? So I apply, for instance, transaction A, right? So I first apply the changes from transaction A, and then I sort of redo whatever I've done for transaction B on top of the result of A. And I do that just sort of optimistically, hoping that there won't be many conflicts. And that's exactly sort of the state of the art. What we implement, what Aptos implements. So Aptos, as I said, they're already a little bit ahead. You know, for them it's in. For us, that's going to roll out probably this year. But in my opinion, you know, after that, if you have parallel execution, the question is, well, how much transactions can you ingest, right? And if those transactions are a little bit bigger, you quickly hit like gigabytes per data or gigabytes of data per second, which becomes complicated, specifically in the decentralized network, right? Which means that you need to have an internet connection which can handle this amount of data. A gigabyte per second is non-trivial. And I think that was the sort of point where Flow's architecture was having first the collector nodes, right, which do the batching, and then the consensus nodes, where that will come sort of into play, and sort of the scalability benefits will kick in somewhere around beyond. Like if you look at Aptos paper, their nodes saturate at about 200,000 TPS, right? That's what a single node can handle. More data, you just don't get into the node. And beyond that, you know, yeah, of course, you know, then you have to sort of do sharded data ingestion, data availability shards. Yeah, hope that answers your question.
Yes, thank you. So anyway, there's like, for now, I think there's like, this is just like bragging rights, because there are no applications sending so many transactions right now, right? So it's just like bragging rights. So another thing it was interesting is I saw about a lot of people about Nakamoto coefficient, like how many nodes have more, like assuming I'm running a bunch of nodes, and all these nodes, the sum of all my nodes are staking more than 33% of all the tokens. It means I'm not very too much decentralized, but I saw some other like Aptos and Sui, they are actually, I mean, the how can I say this? The research behind it was like, okay, there are thousands of people running nodes in other networks, but most of them are not doing anything. The nodes are there, but they are just consuming electricity, but nobody pings them, they do nothing. So I think the execution node on Flow you're talking about, maybe you have like a data center running the execution nodes. So is there like, I'm assuming like you said that you have like 1 petabyte of data, and that petabyte of data can be replicated 8 times, because there are actually 8 execution nodes, right? Is this correct? Yes. So
Yes.
it'd be like just like could be 8 data centers, right?
Yes, exactly.
Okay. Just to see if I understood this correctly. Okay,
Yeah.
thank you. Yeah. Okay, so is there any plan to have like, because right now I'm not sure how much it costs to run a node, but is there any plan to have it like somebody running a node to actually be profitable, or to have it like I know this maybe not exactly about consensus, but is there a plan for people who run nodes to actually at least be even, like electricity cost wise, or not at
Yeah.
all? It's like, or people
No,
are expected to, or people are expected to, for example, okay, I'm running a marketplace or some dApp, so anyway, I'm going to make money via the dApp, so I'm not going to, so this money will cover the cost of the node. If that's where we're going, or it's more like you run a node just to make a small profit of running a node?
great question. Thank you for asking that. I'm always happy if people ask questions about the things I skipped over in the talk, because then sort of we diversify a little bit. Yes. No, I mean, the full answer depends, right? For instance, an access node, it's totally sort of conceivable that you want to run an access node because you have a dApp and you want to manage the data, right? And don't always want to query it. So for access nodes, yes, most likely if you're running an access node, you have a business idea in mind why sort of it makes sense for you to run an archive or an access node, right? And sort of there you handle the cost. If you're running an execution or a consensus node, of course, you're essentially serving the network, and of course that should sort of, you should break even, or even sort of have a small margin of sort of profit there, right? Because specifically that's sort of it's a business model to literally just provide a node, so that's a mature system, right? At the moment, sort of it needs to scale. So in order for nodes to be like profitable and the network to sort of sustain the cost of running all those nodes, you need a baseline sort of TPS, right? And then scaling effects will kick in. And that's sort of the economic balance we have to figure out in the next sort of years as the ecosystem grows, right? As the market matures, where is that going to go, and sort of what's this trade-off factor between transaction fees, right, which essentially then have to cover the node operation cost. So we're working on that. We have a very good economist who's working on that in the background, and we're hoping to figure that out together with you as a community. Where do we want to go, right? As I said, it's a trade-off, and there's no like per se right answer. It's what do we want to do. So please all participate in the conversation, and we're very, very much looking forward to all your ideas, inputs, and where you want to take it. Thank you.
Yeah, thank you very much, actually, Alex.
Thanks, Daniel. Johnny?
Hey, Andrew and Alex. Oh, actually, I have a question regarding the transaction confirmation time. I mean, like taking a view from application users' point of view. So, like, since right now we have different blockchains, and the user can do direct comparison between, the UX layer feeding of the transaction confirmation, right? For example, on Solana, their block time is less than half a second, and as a user, I could feel that the transaction has been confirmed within a second. But on Flow, like, we know that block time is I can't remember. The average block time is 1.5 seconds, right? But like it looks like to me right now the confirmation time takes too long. Sometimes, like in average, it takes about like 5 to 7 seconds. But like in the worst case, I even experienced there was a time like the transaction takes more than 10 seconds to complete. I mean, the measuring is starting from I hit the approve button on the wallet, and then we get a response, either success or failure from the front end. So I think that user experience is really bad for users. So like, do you have any plans, or like, is there any way like that we can optimize the transaction processing time? Because like, since the block time is only 1.5 seconds, I think like theoretically speaking, we can optimize the confirmation time to that goal. Is that correct? Yeah, that's my question.
Yeah, thank you, Johnny. Very, very nice question. So yes, totally. This falls all into the bucket of like there's a ton of optimization room, right? We're building a huge foundation, and that takes a little bit of time. And you're right, other blockchains are very much ahead in terms of how much they've optimized the code. So a good example here is looking at is Aptos. They're essentially running the exactly same consensus algorithm as we are. It's Jolton, right? And they have a block time of 0.3 seconds to 0.5 seconds. We believe that that is sort of the fastest possible you can run if you optimize everything about your consensus implementation, right? So there's no reason why Flow shouldn't be able to run at that exactly the same speed, right? 0.3 seconds. We need sort of 2 child blocks to confirm a block. That would be about 1 second. And so conceptually, that's very much tractable within Flow, right? It's just a bunch of optimizations in the consensus pipeline, in the code. Every line needs to be optimized, which is a huge amount of work, right? And so we're sort of making steps towards that. As you've seen earlier this year, right? We sort of added an improvement of 30%, but it's going to take us some time. And yes, by all means, the transaction latency or transaction confirmation time, it should get smaller. It's a little bit of a longer road, right? But yeah, I totally hear you. Like agree, right? The difference between a fully mature system versus sort of a system which is sort of mature but hasn't undergone all those optimization steps.
Oh,
Thanks,
okay,
good
thanks,
question.
Alex. Yeah, thanks for confirmation. Because I think even a medium or like let's say a short-term goal, if we can make it to let's say 3 seconds, then it's still quite better for the users to believe. Yeah. Okay, thanks. Thanks
Yeah.
for explaining. Yeah, looking forward to it.
Yeah, I completely agree that there is sort of a quite noticeable difference between something like 7 seconds versus 3 seconds. Yeah, please be patient. Or if you want to, hey, if you want to contribute, we're like super happy, you know, for any contributions in that area too. Yeah.
Thanks, Johnny, for the question. Any other last questions?
I had the last question about I saw Aptos and Sui, they have like ABI, like Ethereum also they have an ABI, like being like ADI, but Flow on Flow the Cadence has like Cadence JSON format, like communicating in JSON internally. Like would adding an ABI would be like actually faster, or are there any plans there or not at all? Because I saw like there are actually 2 different things on Flow. Like, let's say that when you write a smart contract in Flow, you can see the smart contract source of the contract. This could be like interesting for the developer to see it, interesting for the people who are signing the transaction to see it. But if they are developers, then they can read it. But on the other chain, on our side, is like if you deploy the same contract on another chain where people cannot read the source code, it's actually like, if you have a business, it's like people will not copy your contract and they will not copy your transactions. They will not copy all the stuff you wrote, right? So it's also like a way to differentiate yourself. Like you will not have a clone marketplace in the next 3 days because people cannot read your contract. So in the early days, it's like critical not to have everybody to copy until you get some users on the space, right? So I don't know if it's like, is that anything you guys are planning to add or not at all?
That's a good question. To be honest, like I'm working relatively focused on the sort of core protocol. So we might not be the best folks to ask. So we're currently in the process of adding a more compact binary format for Cadence. Jordan, do you have more on that?
Only what you literally just said after I raised my hand. I was going to mention the binary format that's coming out. I think that's for data models, though. It's not intended to be a binary representation of the code. And yeah, I do see where you're coming from, but there is also, you know, fundamentally you are ultimately storing some representation of your code on chain, even if people can't read it, they could deploy the exact same code and the exact same API with a different front end, for example. So that there's sort of a limited amount of protection that you can get there. Yeah, did you have more to say on that, Alex?
Yeah, so this is again is a topic where sort of it's maybe also important to talk a little bit about the vision. So at the moment, right, what you deploy on chain is either the source code or a compiled version of the source code, right? We know that from like conventional executable running on Intel hardware or something, you can do something like reverse compilation steps or decompilation, right? So maybe you don't have the source code, but at least you can have sort of some sort of program which tries to extract a human readable version of that source code in a specific language again. And so that is essentially only an annoyance for somebody who wants to copy your code, right? That they sort of have to go under through that step, but it fundamentally does not protect your code from being sort of reverse engineered. The next level to that would be that you work with essentially an encrypted representation of your computation. So there are a couple techniques which I think are sort of maybe worthwhile mentioning. That's one, garbled circuits, which is to cryptographically obfuscate your computation, and the other one is homomorphic encryption, which is also a way. So thereby, the executing platform does not know what they're executing, because it essentially all execution happens in an encrypted space. And so this is a very interesting sort of just outlook. And the cool thing about that is in Flow, I mean, all this sort of obfuscation, cryptographic obfuscation techniques, they're expensive, right? So they cost you in terms of execution, right? And so if you do that on a chain which has limited execution power, you're going to immediately exhaust all this sort of computational capacity of the chain, right? In Flow, that's not a problem. Instead of 1,000 CPUs, you want 10,000 CPUs because 50% of them running, eating that overhead of encrypted computation within Flow. Yeah, no problem. Sure, right? We already have data centers as execution nodes. By all means, go nuts. As long as the computation is easily parallelizable, which in those cases it most likely will, there's no issue. Again, a huge argument for Flow, and sort of it's one of the only platforms where this sort of idea of adding a software layer to encrypt your computation is even tractable. So that's sort of my thoughts on this.
Yes, thank you. Sorry for So maybe we keep another question for next time about. I saw there are like different types of node coming. Would a new node, something like zero knowledge proof node that would actually allow people to transact between them without knowing the addresses? Because you can have like zero, like ZK, just to, for example, to increase like the TPS, but you could also have like ZK nodes just to obfuscate the transactions between what happens. So maybe we keep this for the next session about would the ZK node come to Flow.
Yeah, that's going even further down the rabbit hole. So yes, new node types are coming, or rather, it's more sort of simplifying the framing of the nodes that's coming. We're at the moment not particularly working on ZK zero knowledge sort of within the core protocol team, but we have somebody who's working on this sort of for Bridge. It's not quite the same thing, but wanted to mention that.
Cool. All right, I think we're already a little over time, but thank you everyone for asking questions. I think it adds a lot of substance and a lot of color to what was talked about. And as Alex mentioned, it gives an opportunity to dive into a diverse set of rabbit holes that are always interesting. If you have any more questions, feel free to ask them on Discord, and hopefully, we'll have other demos like this. Other than that, I wish you all a great rest of your week, and if you have any questions, catch you on Discord.